Hello, welcome back to Educator. Today we're going to be talking about biologically interesting organic compounds, or we could call them biomolecules for short. Now there's a reason that if you're going to be studying biochemistry, you typically need an entire year of organic chemistry to prepare you for biochemistry, and that's because biochemistry is the study of organic molecules and organic reactions that are going on inside living systems. And so many of it requires not only an understanding of the structures of molecules, the stereochemistry, and so on, but also the reactivity of different functional groups. And so today we're going to be studying different classes of biologically relevant molecules, and some of which we may have already seen a little bit before, but others we're going to get into a lot more detail. And still, this is all at a level that's not at the biochemistry level. I'm not a biochemist, and this is not a biochemistry course. But it's going to give you an introduction from an organic chemist's point of view in terms of what the significant functional groups are, and seeing if we can understand a little bit how these molecules come together and what behavior they might have in natural systems. So first we'll start looking at carbohydrates. Carbohydrates is another word. An example of carbohydrates are sugars, and so we know of sugars. Those are one of the carbohydrates are one of the things that we can eat and digest as part of our diet, in addition to proteins and fats. And so, in fact, we're going to be talking about all three of those things today. So obviously, all those components are significant when it comes to the metabolism of those compounds and converting those into energy for our body's use. So this is a general structure of a sugar. There are lots of different sugars we can have. This one is described as a hexose because it has 6 carbons. And it's also described as just a monosaccharide. We're going to see that these can form chains. They can link together to form a disaccharide if we have 2 sugar units, and it can actually make long polymer chains. We call those polysaccharides. So this is the structure D-glucose. That's the sugar we know is blood sugar. If you are a diabetic, you have problems with insulin production and sugar level maintenance of a proper sugar level. It's the glucose in your blood that you are testing if anytime you test your blood, and that you're trying to monitor and keep at an appropriate level. And so glucose is a hexose. We see that up here. It has an aldehyde functional group, and then it's a polyol. It has several hydroxyl groups. And this isomer that I've shown here is D-glucose. And if you imagine the mirror image of this, you would have the exact same relative relationship. It would just be the mirror image. The nature typically prepares only a single enantiomer of any chiral molecule, and so sugars are an example of that. The ones that are naturally occurring are described as D sugars, and the way we identify a D sugar is if we draw a Fisher projection like this, where the most highly oxidized carbon is up top, and we draw our chiral centers going down. If we look at the very last chiral center, if this OH is on the right, as shown, then that is a naturally occurring sugar. We're going to call it a D sugar. Now that D, the opposite, the enantiomer, if we were to draw the mirror image of this, that would put all the OHs in the opposite position, including this last one on the left. That one would be described as the L sugar. It's a capital L. It's actually a small cap L. That's different from the lowercase d and L we've seen for stereochemistry. Remember, we talked about optical activity. We described the optical rotation could be a plus or a minus alpha, and those that were a plus alpha we described as dextrorotatory, and a minus alpha is levorotatory. So that little d and little l are just depend on the molecular structure. We have to measure those. We can't predict those, and those have nothing to do with the designation of D and L that we're going to use for sugars and amino acids. So make sure that you keep a note not the same as D and L, little d and little l. So this is D-glucose, and D-glucose can exist in this straight chain conformation, but actually in solution in blood and in at that pH, it actually forms a ring. It prefers to exist in a cyclic form, and we're going to form a 6-membered ring. Remember, 6-membered rings are very easy to form because they have no ring strain. And so the way it can form a ring is what we have here is a carbonyl carbon. The reactivity of a carbonyl is going to be electrophilic. There's a partial positive on that carbon to make it electrophilic. And we have, with all these OHs, we have a variety of nucleophiles. So if we look 1, 2, 3, 4, 5, 6 atoms away, we have a potential nucleophile. So actually we're going to take this bottom, the OH on the last chiral center, and if we bring that up and form a ring, we're going to form a 6-membered ring. Now, we know that 6-membered rings prefer to take a chair conformation, so we're going to draw our chair that way. And if we always draw our chair with this general shape, so we start with a zigzag up and go down, and we always put the oxygen in this top right corner. If we always draw our sugar, our 6-membered ring in the same way, then it's going to be very easy to draw glucose because all of the OH groups are in equatorial position. So it's a very stable molecule. And if we number our carbons, this is the carbon that got attacked. That's carbon 1. And then this is 2 had an OH, 3 had an OH, 4 had an OH, and then 5 has this oxygen, and then it's got also a CH2OH. So this is carbon 5. And up here, we have a CH2OH. So all of the substituents in glucose are equatorial. That makes it pretty easy to identify or draw if you need to. Now let's think about on carbon 1. Carbon 1 used to be the carbonyl. It's now a single bond oxygen, which is going to get protonated, and we're going to have an OH here. And I'm going to draw this. When you think about the stereochemistry of this OH, this is forming a new chiral center. So it's not fixed. You can either draw the OH in the equatorial position, or you could draw it in the axial position. I'm going to draw it as a wiggle line, and that means we can get a mixed stereochemistry. We'll look at that stereochemistry in just a bit on the next slide. And another thing I want to point out about this cyclic form of the sugar is that this carbon, this is a very special carbon. It's described as the anomeric carbon. And that is the carbon that used to be the carbonyl. Notice the carbonyl has 2 bonds to oxygen. Well, even in the cyclic form, it still has 2 bonds to oxygen. Here's one bond, and here's the other bond. 2 bonds to oxygen. That's going to make it very special and unique. And it's going to be something we can pick out of any cyclic sugar. Is this anomeric carbon. There's special reactivity that's associated with this anomeric carbon we're going to be seeing. And if we ever need to correlate that with the straight chain form, we know that that anomeric carbon, that's numbered 1 here, corresponds to the carbonyl carbon. That is either an aldehyde, or some sugars it's a ketone. There are aldoses and ketoses depending on what the carbonyl is like, but glucose has an aldehyde here. Okay, so let's take a look where the OH is. We have different names for the sugars, different stereochemistry. So these are the 6-membered rings of glucose. If the OH is on that anomeric carbon, so I can find that anomeric carbon. Now again, just because I usually draw it in the same general reference, it's this furthest right carbon, but no matter how it's drawn, I see that this is the carbon with 2 CO bonds. So there's my anomeric carbon on each structure. And if the OH is pointing in the down position, we describe that as the alpha the alpha stereoisomer. So that means the OH, the anomeric OH is down, meaning it's in axial position. And if the OH is pointing up, we call that beta. The anomeric is pointing up. And this is in the equatorial position. Okay, so these and when it's in a 6-membered ring, we no longer just call it glucose. We call it glucopyranose. A pyranose means it's a 6-membered ring. It's like pyran is a structure with a 6-membered ring. So the full name for this molecule would be alpha-D-glucopyranose, and this is beta-D-glucopyranose. And both of these exist. Both of them are formed when glucose cyclizes, and both of these exist in our in blood. Now, when it's a cyclic form, how can we tell whether it's a D sugar or an L sugar, the naturally occurring sugar? Well, for the six-membered ring, we're going to have, this was the carbon, this was the last chiral carbon, last chiral center. That's the one that can show us whether we're looking at a D sugar or an L sugar. And so, again, when we always draw this same chair backbone of the six-membered ring, it's not cyclohexane because we have an oxygen in there. When we always have that same backbone, then having the CH2OH group up, CH2OH up, that tells us that it's the D, the naturally occurring. Now, we usually don't see any of the L sugars, but if you ever need to distinguish between them, or if that's part of the assignment is to pick out the L sugar, this is where we would look. Is this last carbon, the CH2OH, is up, so that means it's the D enantiomer that we're looking at. Okay? Very good. Now, glucose can also exist in a five-membered ring instead of a six-membered ring. So here's 1, 2, 3, 4. If we stop at this oxygen, that's also a nucleophile that is in a proper position to attack the electrophile. And remember, five-membered rings are reasonable to form just like six-membered rings. And so what would that look like? The oxygen attacks the carbonyl, and then we would form a five-membered ring with an oxygen in there. And if we keep this carbon as carbon 1 on the right, now again, that carbon will have an OH, but it's of a mixed stereochemistry, so that OH can be pointing up or down. And then we have the OHs. I don't have my stereochemistry right. I didn't draw these down. We draw this kind of like a five-membered ring that's pointing out towards us. We're looking at it from the side. So each of these positions you can draw the five-membered rings. You could draw a position as up or down. So if we tilt this molecule on its side, we see this first OH is down and the second OH is up. And the next OH we rotate it around, and so I think it's pointing up here. I think this is a structure. I have it written out on the next slide, so we'll see for sure. So anyway, we can form a five-membered ring here, and we'll check our stereochemistry. So these are the two examples, and I think I just about had it right. So the place where we can have some variability in the structure and still have it be glucose. These are still glucose molecules. Now we call it glucofuranose, like a furan ring is a five-membered ring. And if we look at that alpha carbon, the anomeric carbon, anomeric used to be the carbonyl, now has two separate bonds to oxygen. And once again, we use the same terminology, the alpha position, because our OH on the anomeric carbon is down, and beta is how we describe it when the OH is pointing up. Okay, so we don't use the words axial and equatorial. That makes sense here because it's not a six-membered ring, but we just look for up or down to describe that. And that up or down, the alpha and the beta, is related to the fact that this is the D sugar. So going back to that six-membered ring, assuming it's the D sugar and that the CH2OH is up, then alpha is also up. So it's actually describing its relationship to that CH2OH. So the alpha and beta won't have the same connotation otherwise.